last time you asked something about this x transpose AY. If this is, say, x transpose A dash Y for all, sorry, x transpose Y, yeah, x transpose A dash Y for some A dash, then whether it's possible to multiply this with, like, pre-multiply with x, post multiply with Y transpose, and say that A and A transpose are the same, without specializing this to the, what you call, EI or EJ. So I said that, think out this, whether this makes any sense. Did you?
Both of them that becomes in-person matrices before and after.
Well, very good. So let's pass this question over to the group N. Okay. So suppose you have this, and then instead of just choosing EI and EJ, you are like trying to multiply it with x. This Y is Y transpose, and choosing x and y as non-zero vectors, and trying to say from there whether this, whether A and A dash will be equal. So where does it go wrong? The question is that, so choose x, say this x and y in Rn. For all x and y in Rn, you have this where A and A dash are in cross. So then what our tells us last time is that choose Rn not entirely 0, and then consider this x transpose times A times y transpose, and that will be equal to x transpose here A y transpose. Okay. From here, can you conclude that? Sorry, let me dash. So from here, since these and these are not identically 0, last time also said that you can conclude from here A and A dash are the same. Can you? Let's suppose. So what was the reason for his conclusion? He thought that these are becoming 1 cross 1. Can they become 1 cross 1? Yes, exactly. So here it is crossing, here it is crossing, and then you are getting this. Even then, perhaps one can try to say that this is n cross n. Maybe there exists an inverse. Can there be an inverse of this? Or again, you can also help, because it was your question. So, what do you think? Can you multiply this with, does there exist an inverse of this? What do you mean, Fallu? So it's primarily a question of group N, but Auto can also answer. Take an example, maybe. You have x equal to, so 0, 1, or 1, 2, maybe, or 1, 1. It doesn't matter. No. If it is 1, 1, you may not recognize what is happening. So maybe 1, 2. And consider then x transpose. Okay. So what it gives? X transpose is 1, 2, and here you are having 1, 2. Okay. What does it give? It's a 2 cross 2 matrix, right? What are its entries then? Can you tell me? Yes? 1, 2. Yes? 2, 4. So can you tell me now whether this matrix is invertible or not? Why not? Wait, let group N answer. Yeah. Determinant is? Why? Yes? Again? Yes, exactly. And so the columns are not linearly independent. So suppose now you have some n cross n thing. What can you tell out X transpose? What? So So the question is that whether this could be invertible or not. Indeed. So what you get? Right. Yeah. So Falgun, I guess that was your logic also, right? So indeed, this the same thing happens there, right? Because every column is a multiple of every row is a multiple of the same row. Okay? Or every column you can also say. Now actually you see something that is this is what is the rank of this? So the question is where is the empty? Well, the next obvious question is that if you get a rank on matrix, can you always write it in this form? That is, if you are given some matrix A, such that A is of rank 1, does there exist X in Rn such that A is X transpose? You said it could be, but I want a definite answer.
Yes, it is.
Why it is?
Because every for any matrix that has rank 1, each of its rows would be a scalar multiple and that could be broken down as well.
Alright, so
I
we have
the row as this row and the scalar multiples as a column.
okay.
And that should be.
But why it should be the same multiples?
It should not be.
Alright, so yeah, think about this. So can I work this out now? And we should prepare again now for the for what were we doing? Spectral theorem, right? So prepare for spectral theorem, proof of that.
So for that rank A is equal to 1, we'll need a additional condition that matrix has to be symmetric.
The matrix?
A has to be symmetric,
Okay,
then we
suppose.
might be able to.
Yeah. So suppose this is this rank equal to 1 and A is symmetric. Great. Yes. So suppose we start with this condition. Then can you proceed? Yes. Why not? What we have here? What? Of course you can, but nevertheless, this is, you said that it's not possible. It's possible.
It's possible, but not in all cases.
Yeah, we are saying that we are giving you a matrix with rank equal to 1 and asymmetry. And then is it true that XX transpose A is equal to XX transpose? It's Falgun, of course that's the point. And then try to finish it. So we should define now what is a non-degenerate form, and before that, well, at first let's define what is a Hermitian space and what are Hermitian forms, because they are anyway necessary when you go to prove the spectral theorem for in the most general case. We should prove it for normal operators, and then everything will fall from there. Hermitian form. So suppose you have a complex vector space. Can I wipe this part out now? I hope you have noted it down. And I hope you will think about this. Let D be a vector space over C. And then you just be a form from V to C, V cross V to C, such that it satisfies this property. At first, conjugate linearity in the first coordinate. In first coordinate. What it means? Suppose you have C, D, and W as your inputs, then that will give you C bar, D, W. And of course you have this one as well. That is, if you replace V with V1 plus V2 or V plus V prime, say, plus V prime, then you just get VW plus V prime so that's the first condition. Then we have, so this is condition 1, then 2, linearity in second coordinate or second input, you can say, because these are not yet coordinate things, coordinates, arguments. And then so that means CW is just C times VW. Okay? Like here we are getting bar and here we are just getting C. Then the second thing is that V comma W plus W prime is the usual thing, VW plus V W prime. So that is the second condition, and the third condition, which finishes this definition, is that it has Hermitian symmetry if you switch the two arguments.
You will get the conjugate transform.
Exactly. That is VW equal to the conjugate of W. If you switch the coordinates, you get the conjugate. So, if a form satisfies all three properties, we call it a Hermitian form. An example, the standard Hermitian form. Cn. What does it mean? This just replaces dot product in R. So if you have say, x, y in Cn, then you define x, y as x bar transpose y. So we wonder why we are not defining the user dot product on C. Right? Because we would like to get something called positive definiteness. And that would require, if you take the product of x with itself, then we should, unless we get something real, if you are taking the product of x with itself, we cannot say whether this thing is positive or negative. So in particular, if we take this one, what we get? X bar transpose x. Right? And so if x is of this form, say some x1 order xn, then this would be just the sum over xi absolute value squared. I running from 1 to n. Right? These are complex numbers now. This is in Cn. So to define positive definiteness or negative definiteness or positive semi-definiteness, well, we can define them immediately actually. So I hope we can wipe this part out. Yes.
Why did you demand conjugate linearity only in the first argument?
We could also work with the conjugate linearity in the second coordinate as well. But nevertheless, we require conjugate linearity at least in one of the coordinates. Because this, I mean, that's what I was trying to explain. So for defining either, I mean, for calling the form a definite form, that is positive definite, negative definite, positive semi-definite or negative semi-definite, we require the product of a vector with itself to be a real number. And that's the necessity of the conjugacy in at least one of the coordinates.
But why do we want it to be a real number?
Yeah, that's what I'm trying to say. Oh no, that's not from this course. That's from the previous one. So, what is this? I mean, suppose let be a form on a real or complex. Well, we require this form to be I mean, symmetric or Hermitian. So let's write it down here. Form on a real or complex vector space V. Then we call this form positive definite if this product of every vector, every non-zero vector itself is greater than 0 for all v in v minus v. Okay. Positive semi-definite if this product is greater than or equal to 0 for all v in v minus 0. Okay. And similarly, you could define negative definite and negative semi-definite. For negative definite, all you recall is that this is strictly less than 0, and for negative semi-definite, you require this to be less than or equal to 0. Now here's a question for you. And in particular for Benedict, if it has already come. No, there is not. V cross V to R, where V, sorry, you can actually take R cross R. It's also fine. Rn cross Rn to R. I was just going to write that where V is a real vector space, and it's clear now that V is a real vector space. So we're having a form such that there exists a V in V with V W equal to 0 for all W in V. The question is that, does this imply V is equal to 0? You see, this is an arbitrary form. I'm not asking this form to be, positive, negative, definite, or positive, or semi-definite. I'm not asking for the form to be any of these definite forms. It's an arbitrary form. The question is that, given such a form, if there exists a vector which is, the bilinear, if you put it in one of the arguments, well, yeah, suppose you are putting in the first coordinate and you are getting this for all of this. Now, is it true that V is equal to 0? Or could you construct some counterexamples? Yeah.
It should be 0 since it's valid for all.
How are you saying that?
Suppose that the form VW is 0 for some, like for a particular W.
Yes.
That in no way would imply. Even that case is possible that V can.
So it's your intuition that it should be 0. So W equal to V, yes. Then, well, even then, the question is that would imply that V equal to 0. Okay, and we said that we are not taking any particularly. So you can say that this form, if this form is positive definite, then V has to be 0. Okay? Or if this form is a negative definite, then this thing has to be 0 because there is a strict inequality there for non-zero. But suppose you are having an arbitrary form. Yeah. Yeah. If we know it's bilinear, then does it imply this one? We only know that it's a bilinear form. How?
Take a different vector such that it's formed with W with some value C.
Yeah.
Add 0 on both sides.
Yes.
Then express 0 as that. So let's say that's V prime. So V prime with W is the same as V with W.
Okay.
But they can't be mapped. W is unique. And they can't be two things can't be mapped to the same value. That must mean V prime plus V is V prime.
Okay.
That means V is the identity of V prime.
Okay. Let's see. Ashwin, you want to say that?
We can take an n-dimensional basis.
Okay.
It is also
Think of things. If you are okay, you are trying to prove this, or
yes.
all right, proceed.
So suppose we have we take n linearly independent vectors of Rn.
Okay.
And V into the matrix of coordinates of those bases
Yes.
equals 0. This implies that V is equal to 0.
It need not. It need not. So no, not that. We saw that this is, any bilinear form would be represented as. Sorry. Where is the yellow chalk? We saw that if A is a ground matrix of the form, then you can write X transpose AY. A is a ground matrix with respect to some basis, a standard basis. Okay. So this is the this will be in this one. Okay. In particular, if it is a standard basis, then you could just put V and W here. Right. Yes, Vayu, you want to say something?
So if we set W as some V minus U for some U in the vector space.
Well, you cannot restrict W. You cannot define W with respect to V because this is perpendicular. Well, we have not defined what is perpendicular.
But what I'm saying, I get what you're saying. What I'm saying is like if we define it to be some vector v minus u, we can always say u is say what w minus v minus w.
So you are taking w as u minus v, okay,
V minus u or whatever.
or v minus u, okay.
So then
And you are saying that this u is varying.
yes.
Okay, and v is fixed.
Yes.
V is some vector which is given to you such that this is equal to 0.
So now we have bracket v comma v
Yes.
is equal to bracket of 0 u.
Bracket v comma v is equal to
Bracket 0 u
0.
by linearity.
Wait a minute. V. So you are. What you are doing here?
What I'm saying is like on the RHS, if you have the form with one of the arguments as 0, then the whole thing has to be 0.
So all you know is that this is equal to 0.
Yes.
And now how u is coming to this?
Wait, is that u or is that v?
This v. I mean, you know that this is equal to 0 for all equals here, all w's here. So in particular, if you put v, you get 0, and then.
Okay. Anything.
So yeah, really one. Okay, just let's check this one. So VW is B transpose AW, right? If in particular, let's say A is the Gram matrix
So is it a
with
symmetric form?
respect to the, yeah,
Is it a symmetric form?
you can assume that as well. If you want to assume symmetry, you can certainly assume. So A is the Gram matrix with respect to the standard basis. Okay. And then you can just put in the vectors V and W because these are the coordinate vectors of V and W. Right? Now, if you take A to be a singular matrix, what happens? And if you, so what I want to say is that, well, yeah. Wait a minute. So you have this one, and then this is some element in R, right? So this, if you take the transpose, this will give you W transpose A transpose V, right? If A is singular, so is A transpose, right? And now, if V is in the kernel, because it is singular, that means that this is belonging to the kernel of A. That is, it is a vector, a non-zero vector that is satisfying A transpose V equal to 0. I mean, there would be some non-zero vector which satisfies this. And if you take this product, then everything reduces to 0. Right? For example, if you choose A to be this one, 1, 1, 1, 1, and choose your V to be 1, minus 1, can you see I mean, this thing just becomes 0. So you put any vector there, you're just getting 0. Alright? So it's possible that V is non-zero, but the bilinear form is giving you an output of 0 for all the inputs in the other argument. So this is not true. So this was the question, and the answer is no. Yeah. Yeah. So suppose A is the Gram matrix with respect to the standard basis. Okay? And then these are just the coordinate vectors, V and W. So this one you can also write because it's a 1 cross 1 thing, but it's equal to its transpose. What is its transpose? W transpose, A transpose, V. Okay? So if you choose this one to be, I mean, if you define the form such that this is a singular matrix, that is its determinant is 0, that means there exists some V such that this is equal to 0. Right? That is some V which is not equal to 0. So if A transpose is singular, there exists V not equal to 0. I mean, A is singular. That means A transpose is singular. Such that A transpose V is equal to 0. And so, if you take that vector and V to be that vector, then its product with everything else is equal to 0. Nipun, is that alright? particular, if you choose A like this and B to be this vector, then that I will put that field here. For every W we get 0. In particular, such a thing would be, this is an example where V is self-orthogonal. Let's define what we mean by orthogonality. Yeah?
Given that the gamma matrix is not singular,
Yes.
then would that imply that V is
Would that imply? Yes. That it's an if and only condition. So after we state it, we can prove this. And the proof is simple. It all depends on the singularity of this. If it is singular, you can choose such a thing. If it is not singular, you cannot.
then only trivial solution.
Exactly. Yeah. And perhaps you can already get it from this expression. So suppose you don't know whether this is singular. Okay? A is singular. Suppose there is some vector V for which this is happening. I mean, we are taking A to be the standard. The Gram matrix should be the standard basis, and you are getting this to be 0 for all inputs W. Okay? Can you say from here whether A is singular or not? So you see, for all the W's, you know that this is going to be 0. Okay? And then what you have to get is that A is singular. Can you compute from here? Let's write down the equation immediately. If from Rn to Rn, well, actually we can go more general from V to V. Say. Such that VW is equal to 0 for all W in, well, such that there exists a V, excuse me. There exists a V in V minus 0 with VW equal to 0 for all W in V. So let B be a basis of V, and let A be the Gram matrix of the form this with respect to B. Then determinant A is equal to 0. That is, A is a singular matrix. So, can you complete the proof? Vikram. The argument is simple. Just look at this form and try to figure it out. We'll come up to this. We'll use this Gram matrix. We'll write the coordinates here. And we'll say that that is equal to 0 for everything. And then what we need to show that this determinant is 0. It's not just a question for Vikram, it's for the entire class, so anybody can answer. So, let A, B, well, we have written down, right? A is a Gram matrix. So let x be the coordinate of v with respect to b. Okay? Then this assumption says that x transpose a y is equal to 0 for all y in Rn, right? And this is again an element in not Rn, sorry, Fn. Where n is the dimension of V. So this is given to you, and this is if and only if y transpose A transpose x that's equal to 0 for all y in Fn, right? So now to show this, what do you require from here? How can you show that the determinant A is equal to 0? You are having this equal to 0 for all y, yes? Shubhanu? Yeah, you can use this one directly. That is, from here, you are trying to show that the determinant of this determinant of A is equal to determinant of A transpose, right? So, yeah, one proceed.
A transpose X is never 0.
A transpose X is?
Never 0 because there does not exist any X source.
So, A transpose X is never 0 if A is non-singular.
If A is not 0,
Right.
except determinant is not 0.
Right.
So it's never 0.
Yes.
So this is 0 for all y. Right?
This is 0 for all y.
So we can construct a y. So it's a non-zero vector.
Yes.
Which y is multiplied to.
Right.
And I'm getting 0.
Right.
So I can always construct a y
Which is?
which is giving a non-zero. Like which is not.
Which one it should be?
Let's say the non-zero vector is like something. Let's say y is 1 0 0 0.
Okay.
That's the first element.
Where this one should be?
It should be at the place where there is a non-zero element.
Wonderful. Yes. So you can choose it directly here. That is, if you know that this is equal to 0, then you can specialize y to the standard basis. Okay? So you are getting the first entry equal to 0, the second entry equal to 0, third entry equal to 0, the nth entry equal to 0. So everything here is equal to 0. That means, I mean, if you vary y over the elements of the standard basis, that will pick up each of the ith entry of this one, right? This is a vector. Okay? So choose y equal to 0, 0, 1, 0. So 1 in the ith place and 0 everywhere else. Okay? And let I vary over one, two, n. What you will get from there then that the ith entry of this is equal to 0, where I is varying from 1 to n. That in particular implies that A transpose X is equal to 0 entirely. I mean, it means all its entries are equal to 0, right? So this one would imply that A transpose X equal to 0 in Rn. Yes. I know that we took V to be some vector in V minus 0. So not all of its coordinates can be 0, right? In particular, X is a non-zero vector. That is, oh well, you can write it here directly, where X is not equal to 0 as it is the coordinate of a non-zero vector. Okay. So that implies immediately that the determinant of A transpose which is equal to the determinant of A. On the other hand, if this A is such that determinant of A is 0, then you can choose such an X and then you can trace it back. So trace back the entire proof just to see that this is equal to 0 for all y, for all the inputs. So this proposition is not true only one way, it's true in both ways. So if A is a gram matrix with respect to some basis of the determinant A is equal to 0, then you can always find such a V such that V, W, this is equal to 0 for all W. So now we should define what we mean by orthogonality and non-degeneracy of a form, or orthogonality of vectors and non-degeneracy of a form. So again, this is a form on V cross V F. Okay. If V and W are in V such that this is equal to 0, we say that, well, we declare this form to be also a symmetric form. Okay? So V are symmetric. It's a symmetric form, or in particular, if F is equal to C, you can also take this form to be Hermitian. Write it as symmetric or Hermitian form. Hermitian in particular if it is C. Symmetry is defined for any field. So if this is true, then we write, then we say, or then we write V perpendicular to W with respect to this form, okay, with respect to the given form. So we just saw that if the form is such that this determinant A is equal to 0, that is the gram matrix is non-singular, sorry, the gram matrix is singular, then a vector could be self-orthogonal. So from here we saw that in particular if the gram matrix of form is singular, well, here we don't need even to mention which basis we are taking, because if you go from one basis to another, the form, the matrix of the form changes by some P A P transpose, right? Or Q A Q transpose, and whatever. I mean, this P is in GLN F, right? So if you take the determinant, and if this is equal to 0, the entire thing becomes 0. You know that this is non-zero, this is non-zero, but now you have, if you take the determinant of this, that will be the product of the determinant of this, and this, and if this one is 0, then the entire thing becomes 0. So if we say the gram matrix of the form is singular, we don't even require to say with respect to which basis. Then there exists a vector V in V such that V is perpendicular on itself. V is self-orthogonal. And this brings us to the notion of degeneracy. Well, at first we must define what is null space of a form.
So shouldn't it be V minus 0 because 0 would be
Ah,
orthogonal
right, yeah.
every time?
Yeah, right. So now we define null space of the form how we define it? Say, well, even before we define null space, we are going to define null space in a minute. But at first, we must define what is well orthogonal space with respect to a given subspace. Later, we'll call that orthogonal complement once we have a form that is non-degenerate, and that will require this relation. So, can I wipe this part out? Orthogonal space. So we are going to define it after we define. We are defining this. Orthogonal space of a subspace. Later we will replace this space with complement. I mean, orthogonal complement of the subspace. Once we ensure that the form is non-degenerate. So we define this. A subspace. W is a subspace of V. Then W perpendicular, we define it in this manner. These are all V in V such that this is equal to 0 for all W in W. So what we are given here, we are given a symmetric form over V. Symmetric or Hermitian form in case F is C. And then we define W part. This we say part as this notation, that is perpendicular. The vectors, all of which are perpendicular to W. We define in this manner. So now the null space of the form is just V part. That is the vectors which are perpendicular on all the vectors V, the ones we were considering in the previous equation. So these are W in V or V in V. Such that this is equal to 0 for all W. Now, non-degeneracy just means that null space of the form is 0. The only thing which is perpendicular on everything else is 0. That's the definition of non. Yeah?
The 0 vector, right?
The 0 vector. Yes. So, a non-degenerate form, we call a form non-degenerate. Sorry. Non-degenerate if V part is equal to 0. So the null space with respect to that form, the null space of that form is a 0 space.
So,
Yeah.
why to define W perpendicular if these two are just are these two just
Well, W is a subspace. And W, we define the orthogonal space. We are going to call it later an orthogonal complement. Actually, just after the next thing, which we can give as a homework, and it's a necessary thing. It's a very nice homework, and you should do it. Don't skip this, okay? So this was for a subspace, and that was for the entire space. W perpendicular. So exercise. cross V to F V are a symmetric form, symmetric or Hermitian form. Form. Okay. Such that it is, well, from here we can immediately say what it means by non-degenerate, being non-degenerate on a subspace. So here goes the first exercise. It's an easy exercise, and the one I'm planning to write down there. So at first, well, I think it will be obvious to say what it means by non-degenerate on a subspace. We know what it means by non-degenerate on V, and if you restrict the form to a subspace and you get that in that subspace, if you well, let's anyway spell it out. What we mean by that is that W intersection W perpendicular is 0. Okay. So W doesn't contain any vector which is self-orthogonal. I mean, which is actually orthogonal on all of W, and in particular on itself. So that, I mean, if W intersection W perpendicular is equal to 0, that means that there doesn't exist such a vector, and in particular there doesn't exist any self-orthogonal vectors in W. So suppose you have such a form, and then, well, the first exercise is that. Exercise, you can call that exercise 2. So exercise 1 should be this one. If a form is non-degenerate on V, does it imply, so this is the question 1, does it imply that it is non-degenerate on W for all W in V? That's the first question. And the second question is that if a form is non-degenerate on W, W is the subspace of V, then for some particular W, for some, so not on all of them, but a subspace, particular W, particular subspace W, does it imply the form is non-degenerate on V? So how non-degeneracy relates, I mean, what is the relation of non-degeneracy of the on the entire space with those on the subspace? That's the point of this exercise.
So what do we need to show in the second question?
Yes. Let this be a symmetric or Hermitian form such that it is non-degenerate on some subspace, non-degenerate on W. W is a subspace of V. Okay. Then V is equal to W direct sum W perpendicular. So then V decomposes as a direct sum of W and W perpendicular, and that's why we call this as the orthogonal complement of W. But to call it orthogonal complement of W, we need the form to be non-degenerate on the space W. In particular, if you are given the form is definite, I mean positive, negative, definite, or I mean if it's a definite form, you know that no vector could be self-orthogonal. So a definite form is non-degenerate on every space, on V, on W, everywhere. So that's all. Okay. Just one more part of this exercise. So this is part 1, and the part 2 is, well, the part 1 is a most interesting one. The part 2 is that if this is non-degenerate on G and W, then, well, this kind of spells out the first exercise actually. Then this is non-degenerate on W perpendicular. So this already gives you a hint for this one. But that's I mean, in particular to this one, this is a very nice exercise. If you couldn't, we would revisit it. So that's all for this. I mean, now the class now. Meet again at 5.